Okay, welcome to the stream, guys. Let me check in the volume. Hello, hello. I think this is loud enough. Okay, so today is again a Rust stream, but I will be building a text editor by following this blog. Hopefully, I will learn some context and some syntax along the way. Yeah, so this is like day 9. I am somewhat familiar with the syntax. Like, I get why do we need match, why is there an option, and stuff like that. And I am kind of familiar with the borrow checker now. The concept is easy to understand, but when you get it in the syntax, it is quite different. So yeah, but I'll get used to it eventually. And yeah, I hope I become a Rust developer. Cool, so let's get started. Let me decrease the music volume, or I think it's fine. Cool. Okay, let me build your own text editor. The old, complete but outdated version of Hecto is available here. You are looking at the 2024 version of Hecto, which is still unfinished. You can follow the progress of the rewrite here. Once it's done, this notice will be deleted. Okay. It's a re-implementation of Antares Kilo in Rust and a remix of Page Rutin's tutorial for the same thing in C. It's somewhere north of 1000 lines of Rust in a few files with a few dependencies, and it implements all the basic features you expect in a minimal editor, as well as syntax highlighting and a search feature. These posts walk you through building the editor and learning Rust in multiple small steps. For the first steps, you'll add, change, or remove a few lines of code. Most steps you'll be able to observe the changes you made by compiling and running the program immediately afterwards. Once you have built up a solid understanding of Rust, you'll get a description of what to solve next and have the opportunity to try it out before you compare it to my own take on the solution. I wrote this tutorial coming from a different corner of the engineering world to obtain a deeper understanding of Rust. If you are in a similar situation, this tutorial is for you. If you already know Rust but wonder about the ins and outs of text editors, this tutorial is also for you. I explain the cool. Feel free to skim or skip the pros, as the main point of this is that you are going to build a text editor from scratch while learning Rust. Anything you learn along the way is a bonus, and there's plenty to learn just from typing in the changes to the code and observing the result. Yeah, that okay, makes sense. So I'm at the introduction. I need to, what is a change log? Whatever. Okay. This post last updated 2 days, 2 hours ago, but if you wish to just read instead of coding, that's fine too. This tutorial is long and very deliberately so. If you want to build the same text editor in Rust but with less prose and less sidetracking, have a look at Pound. However, once we get to the point where I create assignments for you, it will be easier for you to skip explanation and just go from one assignment to the next. Yeah, I'm ready for a long tutorial. Okay. Cool. Don't you love a fresh start on a blank slate? Yep. I've already installed Rust. Which version of Rust is this guy using? Didn't mention, I think. Okay. Okay, we'll use this program to get started with Hecto. Delete your previous this and the executable this. Okay, in a directory where you'd like Hecto to come to life, type the following: cargo init Hecto --vcs none without git support. If you want to use git in this, yeah, okay, cargo init Hecto. Do I need version control? I'll do it manually later. Done. Okay, there is no tree command. Okay, I'll just do nvim. Boom. Should have done tmux and then do this, right? And here I'll open up my nvim. Perfect. Yeah. Yes, I can even run this by using cargo run. Yep, it works. Running this command adds a few more lines, which we'll look at it in a second, and puts an executable called Hecto into the folder. What? It created a new folder called Hecto, populated with some files. We will go through most of them in a bit. The most interesting one is called the main. Let's look at that one. When you open it, a main function hello world. To use cargo, make sure you are in the Hecto cd cargo init Hecto, and then run cargo build in your shell. Cargo is not silent as Rust C was, and will produce output that looks a bit like this. Okay, so if I do cargo build here, it will do something. It will build in a target file. So if I go to target, there will be two things. Yep. What? How to execute? Do I need Rust C? Okay. Done. Our Hecto directory now contains a whole bunch of things. Some of them are hidden. The specifics might look different on your machine. A folder called src, two files named cargo and cargo.log, a folder named target with some hidden files in it, and a folder named debug. That folder contains more files and folders, and our executable Hecto. The source folder, where are all source files? This is too basic, brother. This file follows a config format.toml and is used to tell the compiler a few things about the code and it's supposed to compile. We will take a closer look at the default one, a few paragraphs now. So cargo.log and cargo.toml files are similar to package.json and package.lock.json. I think so, yeah. They just define what dependencies are there in this project, and yeah, that's all, with their versions, of course. Build targets. Let's take a look at target and its contents. Cargo supports multiple so-called build targets. The one that is used as the default is debug, meaning that the final executable is mainly targeted at us, the developers, and not at actual real end customers. Another valid target would be release, which is the opposite, something to put it into the hands of the customers, not only for developers. Okay. Done. Once you do, you will notice that another folder appeared in the target folder, aptly named release. Wait a minute, what does it mean? The executable is targeted at someone. Doesn't it only print hello world regardless of who uses it? Well, kind of. First of all, the Rust compiler tries to be very accommodating to developers and end users. Therefore, it treats debug and release builds differently. We will encounter a concrete example later, but there are several types of programming errors where Rust assumes that you really did not do this on purpose. If a debug build encounters this kind of error, the program crashes, which is the most extreme thing Rust can to tell you just how wrong you have been. But Rust does have a way to recover from these errors and can continue with wrong results though, but it can continue, and assuming that for the end user a wrong result is bad but a crash is worse. The same error would not crash the release build. Okay. Secondly, the compiler can perform various optimizations under the hood to make sure that the results are faster, but these optimizations take time and make compilation slower. Who compiles all the time? Developers. Who compiles? Never. Users. Therefore, debug builds disable the optimizations to prioritize speed in development, and release builds enable them to prioritize speed in executions. Lastly, the executable does contain code other than just hello world, and Rust adds information to the debug build which will help you debug any issues quicker. This information isn't needed for customers, therefore it can be excluded from the release build. Cargo also tells us as much during compilation. The final line for a debug release reads like this: finished dev. Okay, yeah, it did. Finished dev profile unoptimized plus debug info. Okay, we are learning quite a lot here. While the release build, on the other hand, ends its compilation with, so if I do cargo build hyphen release, yeah, finished release profile optimized target. Okay, makes sense. Let's take a closer look at the debug info, but let's not mess with our new and already beloved text editor code. Instead, head over to the Rust playground, which helpfully already contains our hello world function. On the top left, you see some buttons: debug, then stable, and then Click these to enable backtrace. Then change the code in the playground as follows: Panic triggers a crash, plain and simple. Click on run to run it, then click on debug, change it to release, and then run it again. You will notice that the release build generates the following output: running target release thread main panicked here, stack backtrace. The debug output looks something like this: Rust began, unwind, panicking. Okay, some more information basically, and it is also telling the line at which everything is happening. The backtrace is, I think, all the function calls that led up to that error. Without understanding stack traces yet, you can immediately see that the debug output contains more information than the release versions. Understanding the call stack, so the order in which functions have called other functions, then some more until one of them crashed, can be tremendously useful. Build artifacts, so that explains the folders, but what about the stuff in there? That is not hecto. Let's investigate something to further our understanding. Back in the terminal, run the following commands in order. Okay, so currently we have source and a target folder. So if I do cargo clean, I believe it should delete the target folder. Yes. If I do cargo build again, it is building. If I do it again, it will say that it is already built and there is no change in the code, so why build again, right? Yep. There is no compilation, just finished, done. Yep, the second runs as before. During the third, does not output compiling as it did before. This is because cargo can tell that the current version has already been compiled if the main was not modified since the last compilation. If main rs was changed, then cargo recompiles. Once your code base grows, this will become more useful, as most of the components shouldn't need to be recompiled over and over when you are the only making changes to one component source code. All of the extra files in the target directory are build artifacts, which enable cargo to do subsequent compilations more quickly. Find more on this in cargo's documentation. Since it's very common that you want to compile and run your program, cargo combines both steps with the command cargo run. Try changing return variable in the this, then hello, then cargo run, then you should see it compile. Boom, done. Let's take a look together at the code. Open this step on GitHub. If you follow the link above, you'll see an annotated commit. It shows you all the changes that have happened in the code between the previous step and the current one, with some comments directly on the line with the relevant code. In this case, I am describing the contents of the cargo.toml in that commit. Okay. Yeah. Initialization. So he's explaining each and every line here. Okay, makes sense. You can see explanations directly on the code I am referring to, making it much easier to understand the code change. You can directly ask questions or comment on code fragments you don't understand at the beginning. It might be tiring for you to switch back and forth between this tutorial and GitHub. However, as soon as we have learned the basics, I'm no longer going to show you what I did up front so that you can repeat it. Instead, I'm going to tell you the assignment first and later show you what I did to solve it, so you'll switch to GitHub less often. I will link to a lot of additional material throughout this tutorial. Here's a convention I will stick to. Information crucial to understanding the tutorial will be either on the GitHub commits or directly here in the text. Any other link that is not clearly identifiable as a step on GitHub contains optional information that you can skip if you are not interested. Wrap up and outlook. In this chapter, we have installed Rust, initialized Pierpont project, and familiarized ourselves with it. We now know how to compile code by hand with Cargo and have a good initial understanding of Cargo and the files it produces. Most importantly, we can build stuff and clean up behind us if need be. We also met the Rust playground, which will sure come in handy once we want to investigate new things in isolation before we put them into action. We are going to build a program which reads user input, prints it on the screen, and exits on pressing Q. That alone will hold a ton of beginners learning for us. This pose at one point you will be able to edit Hecto with Hecto, so you won't even need a text editor anymore. Rust supports asynchronous code, which we won't cover in the tutorial. In this case, it's perfectly possible for main to end, but not pass control back to the operating system yet. Not sure about you, but creating an actual real-world grown-up executable was, and somehow still is, a magical moment for me. Okay, good. Let's get back to chapter 2. How do you go next, brother? Okay. So here in this GitHub is explaining just what if you don't use, you won't have this. Okay. Cargo square brackets denote sections. The package section configures some things which will then influence the final executable program. It sets the name of the executable to what you have provided when running Cargo init. Okay. And the first version is 0.1.0 by default. We won't touch these values over the course of the tutorial. The addition tells Cargo which edition of Rust to use. Think about this is which file, cargo.toml. Okay, let's see. Okay, edition is 2021. What the fuck? Okay. Cool. Got it. Let's try and read key presses from the user, remove everything in the main.rs and replace it with the following code. Let's go. Making changes here. So in function main, what is he trying to do? For b in io stdin dot bytes. So I think he's taking user input using stdin, he's converting them into bytes, and then he's iterating over each byte, right? Let c equals b dot unwrap. So that byte is being typecasted as a character here, I think. Print ln. What do we need to print? We need to print c. Perfect. And we need to just import this io self read. Okay, let's write this and run this. Cargo run. Now I need to type something. I am epic. Yep. Play around with that program and try to find how it works. To stop it, press Ctrl C. Once you think you have sufficiently understood the program, head over to this tab for an in-depth explanation of the code and syntax. This is a good tutorial, man. I'm already loving this. In layman's terms, this line tells Rust from the standard library, I want to use input and output stuff. This line is a shorthand for this. We will use IO below, but we won't use read, so why import it here? In short, it's a trait. Something we will revisit a bit later. In a nutshell, read brings the implementation for bytes with it. Try removing it and see what happens. Bro, this guy is too good at teaching. What does it what is he, man? Is he a professor? Bro. Runner and retro games engineering manager. Wow, cool guy, pretty good, man. Very nice to do, very detailed, cares about the learner. Okay, so what this line does, it can be stated as, for every byte you can read from the keyboard, bind it to B and execute the following block. This is what individual pieces do. IO represents input output. We imported this above. stdin calls the function stdin on IO, which represents the standard input. Calling bytes on stdin returns something we can iterate over, or in other words, something which lets us perform the same task on a series of elements in Rust. Okay. Using an iterator allows us to build a loop with for in combination with bytes. We are asking Rust to read byte from the standard input into the variable B and to keep doing it until there are no more bytes. These two lines basically print out the character that was read. We'll describe this more thoroughly in a bit, and I promise I'll explain unwrap and println in due time. Perfect. If you've guessed that the code would print out any character you type on a new line, you would have been wrong or half right. This is what the program does, but it doesn't immediately get the characters from the terminal for processing. When you run Hector, your terminal gets hooked up to the standard input, and so your keyboard input gets read into the B variable. However, by default your terminal starts in canonical mode, also called cooked mode. In this mode, keyboard input is only sent to your program when the user presses enter. Okay, this means that our program will let you type whatever text you want, and once you hit enter, it outputs the same text with every character in a new line before it waits for the new input. If you press Ctrl D, you tell stdin.bytes that the file it's supposed to read has ended. This behavior is useful for many programs. It lets the user type in a line of text, use backspace to fix errors until they get their input exactly the way they want, and finally press enter to send it to the program. This is how terminals work and has nothing to do with Rust. But this does not work well for programs with more complex user interfaces, like text editors. We want to process each key press as it comes in, so we can respond to it immediately. Press Q to quit. To demonstrate how canonical mode works, we'll have the program exit when it reads a Q key press from the user. To do so, add the following code below println. So if we go here, before println, if C is equals Q, then break from the loop. Okay. But it will just so if in my text, if there is any Q in between, it will just stop there, right? What? The break statement will end the for each loop, and it does so if the character that is read is a Q. To quit this program, you will have to type a line of text that includes a Q in it, and then press enter. The program will quit, read the line at the time. Neither will the program end immediately once you press Q. You have to hit enter sometime after, nor will it process anything that comes. Entering raw mode. What we want is raw mode, and we are going to use a dependency to change our terminal to it. External dependencies in Rust are called crates. and the one we are going to use is called cross term. We add cross term by running the following command. Okay, let's first run this cargo run. This is my text without the cursed letter Q, but this won't print. What? Oh, I didn't write it, man. Sheesh. I am a dumbass. Fuck. This will print. This won't print. Yep. Perfect. What we want is raw mode, and we are going to use a dependency. So cargo add cross term. Cargo add cross term. This produces the following. Cargo updates its index from crates.io and then adds cross term to the previously empty dependency section of the cargo.toml. So if I see cargo.toml, yep. Next time you run cargo build, you will see that cargo will build much more than just hecto, as it now also builds cross term and the dependencies used by it. Now let's use our shiny new dependency by replacing the contents of main.rs. So in here, what we need to import, use cross term terminal enable raw mode. Use cross term terminal disable raw mode. So in function main, enable raw mode dot unwrap. What does unwrap function do? Okay, he'll explain in a bit, right? So enable raw mode dot unwrap, and then if C disable raw mode dot unwrap. If C is Q, disable raw mode dot unwrap, right? Try it out and you will notice that every character you type in is immediately printed out, and as soon as you type Q, the program ends. Okay. Let's see. Clear. Cargo run. Here is building something. Okay, it is a build. Let me print A. What? Nothing is happening, brother. Yeah, it is printing. But there is a space. There is a space, brother. What does this space represent? Oh, new line. Damn. Try it out, you will notice that every character, Okay. Yeah, let me disable raw mode. Yeah, we can import them in both in one line, right? Disable raw mode, and we just delete this line. Perfect. Yeah, we are importing two functions, I think. Yep. We enter raw mode with this method. Bear with me, unwrap will be explained. Here we disable raw mode again, the way way it's implemented right now, we only disable raw mode if we exit using Q, and we do not disable it if we exit in any other way, which will mess with your terminal. Play around with it to see how much it's going to be messed up. We'll refactor this soon though. Okay, so if I don't press Q and do Control C in between, it will be something else, you mean? So if I do something, I am printing some letters, but if I do Control C, Control D, nothing is happening. Oh. Okay. Now is also a good time to discuss dependency management a bit more in detail and connect what we see here with a few things from chapter 1. Using dependencies means that we can focus on our coding task without having to reinvent the wheel over and over again. The cargo.toml plays a strong role in this. Not only do we list dependencies there, but if we are building a library function ourselves, we can use the cargo.toml to provide additional information about our package should we decide to publish it. It's normal and sometimes unfortunate that dependencies have other dependencies, and these other dependencies depend on other things too. This implies that we essentially need to trust the author of the library to be a nice person, have trusted or checked that the author, if their dependencies are also nice persons, and so on. At this point, Cargo's ability to selectively recompile parts of the code which have changed comes in pretty handy. As recompiling the whole thing might take a bit, the compile time is not bad yet. Okay. That would be concerning after adding just one dependency. If you poke around in the target directories as we did in chapter 1, you will now also notice that the aptly named folder deps is now filled. Let's see. CD target ls. There is nothing here, brother. What? There is no deps, brother. Is it under debug? Yeah. ls deps. Yeah, something is there. Cool. Yeah, deps will be filled. As you can also notice that the resulting executable for a release build is much smaller than the resulting executable. Okay, let's also try to understand the final piece of the puzzle which we omitted in chapter 1. The cargo, that file also contains as described in the GitHub step. Cargo is nice enough to upgrade versions which do not include breaking changes. Let's say crossterm introduces a bug fix but stays otherwise unchanged, then this behavior means that we only need to ask Cargo to update its index by running cargo update. Then a subsequent build would be used Let's say you have successfully released Hecto and it is used around the world. Then someone submits a bug report and you try to reproduce it. You open your old Hecto codebase, rebuild it, and you can't find the error. This means one of the following happened. You didn't reproduce it properly. Your machine is different than the other one. That's where the error is coming from. The bug was due to a faulty dependency, but that dependency has fixed the bug which Cargo downloaded, meaning your new version doesn't have it. This is pretty annoying. The cargo.log attempts to solve one of these problems by providing you with a very specific fingerprint of all the dependencies that went into your build. You can build based on the dependencies in the cargo.log by using cargo build -logged. Okay. Oh. To enter raw mode, we simply needed to call our dependency to do it for us. Neat. What crossterm does for us is that it first gets the attributes of our terminal under the hood, disables a lot of them, and sets these new attributes. Crossterm uses methods from libc, which represent raw bindings to platform system libraries. Using them directly at this point would require us to use Rust functionality and concepts we don't understand at this point, to modify obscure terminal settings which we also don't understand yet, so a library function it is. If that doesn't satisfy you, maybe the following will. We will learn the required Rust concepts later in this tutorial, so once you've completed it, you should be able to set raw mode by yourself. The underlying terminal attributes needed for raw mode are explained in depth in the original Kilo tutorial. The Rust way of doing this isn't all that different. If you want to understand the theory without deep diving into the implementation details, you can use cross terms implementation as a starting point. To get a better idea of how input in raw mode works, yeah, okay, let me take a break here. Yo, I'm back, I'm back. I went for a little snack. Okay. So, where were we? We were on here, right? Let's print out each byte that we read. We'll print each character's binary representation, its numeric ASCII value, as well as the character it represents if it's printable character. We do this by changing this, okay? Mm-hmm. Let b equals b dot unwrap. Let c equals b dot as character. Mm-hmm. If what c dot is control, binary ASCII I think slash r means raw string, else println binary ASCII 003, and this is the character representation. Okay. Okay, let's see what we did here. So we are trying to see if it is printable character, then we print it as a character. Otherwise, we just print the binary and ASCII value. Println is a macro which is code that will produce other code. The result will be this, replacing this with the display representation. Okay. We are no longer using C, but also the direct byte representation P. But wait a minute, didn't we declare B already in the loop above? Yes, we did. Rust allows variable shadowing so that we don't have to keep two variables B and B unwrapped around. From here on out, in this block, B represents the unwrapped byte value. I'll swear I'll explain. Okay. As does as a typecast P, which was a byte. Technically an U8. We'll get to this bit later. We can be safely cast to a character, otherwise the compiler would complain character types are printed out differently. Tells us if C is a control character, which means that we wouldn't want to print out such as backspace. Among other changes which I'll describe below, we have added /r at the end of the new line. This is carriage return. We'll get to this in a second. As explained above is a macro. That macro uses another macro format which will take a string as well as other parameters and then assembles them together to a nice looking string which will be printed out eventually. Previously we only used curly braces, which was using the display representation of whatever we are passing. Now we are doing a few more different things. Let's break them down. So 008B takes the 0th argument behind the string, so B. It takes that argument and uses its binary representation denoted by B before the end of the curly braces. This B has nothing to do with the fact that the parameter is also called B. What the 08 in between means that the binary representation padded with zeros to a width of 8. That padding makes the output more readable. What the hell is this? I didn't understand this. Takes the 0th argument behind the string, so B. It takes that argument and uses its binary representation denoted by the B before the end of the curly brackets. Okay. And 08. Okay, so this B means that this is a binary representation, and 08 means that the binary representation is padded with zeros to a width of 8. So the width of one binary, like one character, is 8 and it is padded with zeros. Perfect. That padding makes the output more readable. Okay. Also takes B. This time we'll output it more or less as is, but we pad it with zeros to a length of 3. Now takes the first argument, so C, and outputs its debug representation, which is supposed to be a developer facing. See what happens if you switch between debug representation and the representation we used previously. The padding for both binary and non-binary representation makes the output more readable, especially when comparing. Okay. Okay. Okay, so it is printing the binary, ASCII and character. But if I do like numbers, it works. But if I do backspace, it won't print character. If I do space, comma, control, no, alt, option, no. Okay. Perfect, delete. What? I don't know. Head over. Before we play around with this together, let me quickly tell you some fun facts about printing things in terminals. But first, typewriters. Typewriters worked like this. A paper sheet was fixed on a drum, which in turn was fixed on a carriage. Every time you'd hammer on a key with a character, a mechanical stamp mechanism would stamp the corresponding character onto the paper and move the carriage a bit to the left. When you got near to the end of the paper, you would hear an audible ding telling you that you should now care about a word break as the end of the paper was approaching. Then you would need to rush then you would need to push a handle to the right. That handle did two things: it moved the carriage so that you could start the new line fully at the left, and it turned the drum so that you wouldn't override the previous line but started a new one instead. All three concepts, the bell, the turning of the drum, and the moving of the carriage, are still present in computers, though historically these concepts made their way via teletypes to computers. To come back to Hector, you might have noticed further up that println did start a new line, but it didn't start it on the left, as if on a typewriter we only rotated the drum but did not move the carriage. What? You might have noticed further up that print Ellen did start a new line, but it didn't start it on the left. What does that mean? By the way, we are a bit indecisive in our code about which parts we want us to handle, like the new line which is added for us by println, and what we want to do ourselves. Now let's use our new program to learn a few things. Under the hood, the characters are just numbers, and numbers are represented in memory. Okay, I'll read this in quiet. Let's wrap up this chapter by improving the way we handle errors. As in, we didn't handle them before, but now we want to. This is also where I'll make good on my promise and explain the occasional unwrap we've met along the way. First, some short theory. In many programming languages, if a function encounters an error, it will not return but instead throw an exception, which you can catch further above and try to recover. This means that we effectively have two ways a function can return controller to whoever invoked it, either by returning a value or throwing an exception, and both of these things require different pieces of code to handle, making it harder to reason about the code. In Rust, you can return errors from functions just as any other return value, allowing for a much cleaner way to handle exceptional cases. To do this cleanly, Rust has the concept of a result which comes in two variants, OK and error. Here is the metaphor that we are trying to go. Let's say I owe you money and you request that money from me. Then either I give you the money or I tell you that nope, I have nothing to give it to you. This is my way of telling that you that requesting money owed is a function that either returns you some money or it throws an exception. Note that returning €0 in case I have no money would be invalid in case I actually owe you money. So throwing an exception here comes closer to the mental model of getting the money owed. Now instead of money, I return you a box that, and I do that both when I have money and when I have no money. In case I have your money, it's a pink box labeled OK. Wrapped inside, you will find the money you need. Otherwise, it's a black box labeled error. That box contains information about why I didn't give you anything. So now what unwrap does is to stay in the metaphor to assume the box is pink and take the result out of it. If the box is black, your program will stop then and there. The behavior we want is that we pass errors upwards as far as we can, let them deal with that black box up there, and at the highest level, when there is no one left to pass the error to but ourselves, but we would finally abort the program. Okay, so he's just teaching us match. Okay, this will be quick, right? So in here, inside the loop, right? Yep. Here I just need a match B. Does match end with a semicolon? No, it doesn't. It's just a block. So in match B, if it is OK B, then we do all of this, right? We need all of this, and then we cut it, and then we paste it here, right? I think this is a pretty bad way of intending, right? Intend in visual mode Vim. Enter visual, then select, then press. This is oh, I am so bad. We select. What? Oh shit. What? Oh damn. We done. Okay, cool. So if it isn't okay, then do all of this garbage code. Otherwise, if there is an error, then we need a comma here. We need to say that error, and then we just print that error, right? Error, done. So match ends here, right? And this is the loop. Let me just quickly fix the indentation. Done. Okay. This statement is not surrounded by a body. So what's the matter, brother? Hmm, I don't need a comma. Is that what you're saying? Okay, our program works. So match, how does match work? So match B, okay, error. We don't need a comma here. What? We need a comma at the end. What the hell is this? Cool. Okay. Wrap up and outlook. In this chapter, we learned about dependencies, reading user input, the basics of error handling, and a surprising amount of information about how terminals and typewriters work. If you found this chapter a bit light on coding, then you have something to look forward to. In the next chapter, we are going to build foundations to stay as close the okay, however, using it is a crucial part, so omitting them entirely would be pointless. These links. We have sidestepped the problem here. Everything I said about ASCII so far is true, but Rust uses a superset. We'll get to the joy of text encodings later in the tutorial. Bro, I'm loving this tutorial. I think this is the best one I have encountered so far in Rust. I highly recommend this blog. Okay, I think this is it for today. Yeah, this is it for today, guys. If you like the stream, that's good. And yeah, I'll see you next time. Thank you for watching.